All right. Uh, Welcome everybody to the Georgia Tech Graph Theory Seminar. Our speaker today is Rose McCarty from University of Waterloo, and she will tell us about unavoidable dense-induced subgraphs.
All right, thank you for the invitation. All right, so let's go ahead and get started. I want to start with this old theorem of Erdos, which says that for any d and k, there exists a graph with average degree at least d and girth at least k. So this is really well known, and in fact, you can do a bit better and find graphs with large girth and large chromatic number. But at first, whenever you see this, I think it's surprising because it says that you can find really dense graphs in this sense, that the average degree is at least any given constant. That's what I'm going to mean by dense in this talk. But yet they locally look like a tree. Since the girth is the size of a shortest cycle, this means that if you look at any one vertex and look at its local neighborhood surrounding it, that you just see a tree. So locally, it's as sparse as you can get, even though the graph itself is quite dense. And so it's going to be important later, so I want to talk about how you prove a theorem like this. So since it's Erdos, a random construction works. So you start with a big enough clique, and then with an appropriately chosen probability, you include each edge independently at random with that probability. So maybe this edge gets included, maybe this edge is not included, and you keep on doing this for every edge, and eventually you end up with some graph. And now you can show that in expectation, it doesn't have many different short cycles. So this graph has exactly two triangles, this triangle and this triangle. And so now if we delete one edge from each triangle, in expectation, this is going to be a graph with high average degree. And also, because we deleted all triangles, this particular graph has girth at least 4. Right? The girth goes up whenever you delete all short cycles. So we'll see this sort of idea showing up again later. So in 1983, Thomassen conjectured this really exciting idea, which is not only do these graphs exist, which is sort of surprising already, but also they're unavoidable in the sense that every sufficiently dense graph has one of these graphs as a subgraph. So what I mean by that is that for any d and k, every graph of average degree sufficiently large as a function of d and k has a subgraph of average degree at least d and girth at least k. So I'm going to be using this notation throughout the talk. So anytime there's some function, what I implicitly mean is that for any d and k, there exists some number f of dk such that the rest holds. And I'm just going to be writing that as shorthands throughout. And this is just a picture to say what the graph could look like. The particular graph doesn't have any 3, 4, or 5 cycles. And so this is just an example. Pretty dense graph with girth at least 6. Okay, so the previous approach that we went through works not just for cliques, whenever you include edges independently at random and then delete one edge from each short cycle. That approach also works for regular graphs. And so this is going to show up later. But one thing that makes Thomassen's conjecture really difficult is that there are graphs with arbitrarily large average degree, but no little d regular subgraph for any little d at least 3. So you really can't reduce the case of regular graphs. Yeah, Anton?
Rose, there is a question. I don't know if you can see the chat. Can you?
Yes. Should this be induced or not? We're going to talk about that. I think that's the next slide. So thank you for the question. Yeah, so to start with, the literature is focused on just finding subgraphs. And so the main focus is going to be what if we want to find induced subgraphs. And there, we're not allowed to delete edges. We're just allowed to delete vertices. And so you get 2 problems right away, 2 sort of obstructions for Thomassen's conjecture being true for induced subgraphs. And those are cliques and bicliques. So any reasonably dense subgraph of a clique has a triangle, and any reasonably dense induced subgraph of a complete bipartite graph or a biclique has a 4 cycle. So these are obstructions. You can't find induced subgraphs of a clique or a biclique with large girth and large average degree. So the main conjecture that I want to focus on today is that these are the only obstructions. So that Thomassen's conjecture holds for induced subgraphs as long as you exclude a clique and a biclique. And so the more formal statement being that for any d and k, every graph of sufficiently large average degree is a function of d and k as either kd, kdd, or a graph of average degree at least d and girth at least k as an induced subgraph. And so now here are the pictures, right, where, I mean, this one's always induced if you find it, right? But saying that you can find these in an induced subgraph means that you can find these after just deleting vertices. All right, so the first thing to notice is that this is actually stronger than Thomassen's conjecture. And the reason is that construction that we went through at the very beginning of the talk. I said that that works for regular graphs. And so in particular, if you start with KDD, then that construction will work. Actually, so first of all, let me say that every d-vertex graph is a subgraph of KD, and so KD helps us a lot, right? But since KDD is regular, we can also find subgraphs of large girth and large average degree in KDD by, again, just including each edge independently at random, and then deleting one edge from each short cycle. That would work. And so there's two things I really want to focus on in this talk. And the first thing is to try and convince you that this conjecture should actually be true. I think it's surprising. I mean, whenever I started looking into this area, I didn't just immediately conjecture this or anything. I think it's pretty surprising, but I think that the evidence now is pretty good. In fact, almost as good as the evidence for Thomassen's conjecture. And the second thing is I want to talk about what makes Thomassen's conjecture hard. In particular, I think that the fact that this is a conjecture says something about why Thomassen's conjecture is hard, but we'll see what I mean by that later. Okay, so first let's start with what is known, and that is that for both of these problems you can reduce them to the case of bipartite graphs. So it's an easy proposition. I think that we actually did this in Jing's graph theory course that I took at Georgia Tech. So it's a nice proposition to say that for any d, every graph of average degree at least 2d has a bipartite subgraph of average degree at least d. So for every vertex independently at random, you flip a coin and say color it blue if you get, say color it blue if you get heads and red if you get tails. And then in expectation, at least half of the edges go from a red vertex to a blue vertex. And so if you just take that as your subgraph, then that proves the proposition. So that's really nice. But what's incredible is that really recently, Quantelesser, Sudokop, and Tram proved an induced version of this. So what they proved is that for any d, every graph of a sufficiently large average degree is a function of d, as either KD or a bipartite graph with average degree at least d as an induced subgraph. So typically you really think about this as saying exclude a clique, and then you can find your induced bipartite subgraph of large average degree. So this is really nice. This is sort of incredible. This is something that made me start working on this area in general. And this was actually asked as a question whether or not this could be true by Kuhn and Ostis in 2004. And really recently by Esper, Kang, and Thomassen in regards to some questions on a version of list coloring. Right, so this is a really nice theorem. Let's go through the pictures of what it says. So it says either you can find a clique as an induced subgraph, or by just deleting vertices, you can find an induced subgraph, which is bipartite and has large average degree. Okay, so that's like the first step. And the second step would be to remove 4 cycles, because those are the smallest cycles in a bipartite graph. And so there's a theorem of Kuhn and Ostis from 2004, which says that for any d, every bipartite graph of sufficiently large average degree has a subgraph of average degree at least d and no 4 cycles. So they showed that you can get rid of 4 cycles. And again, the picture is that you take a subgraph to get rid of the 4 cycles. And this graph actually doesn't have any 4 cycles, but I'm not going to challenge anyone to check. Okay. And so the main theorem from the paper that I'm discussing is that this holds for induced subgraphs, as long as you don't have a big biclique. So for any d, every bipartite graph with sufficient large average degree has either KDD or an induced subgraph with no 4 cycles. Pictures are either you get your big biclique like that, or by just deleting vertices, you get rid of all the 4 cycles while keeping the average degree at least d. It's of course hard to draw a picture of these because the graphs end up being very big. So for the same reasons as before, this also implies the Kuhn-Ostis results. But also the proof is based on a different proof of the Kuhn-Ostis results by Delmonica, Kubek, Martin, and Rodel. And I'll talk about how it relates and what is new about the proof there. But again, the main focus of the talk, I think, is not the proofs, but just the facts that this general conjecture should be true. Okay. So the other evidence for the general conjecture being true on induced subgraphs is that it holds for regular graphs. So I think that regular graphs are interesting to look at because if you look at cliques, they're just the densest graphs, right? And the induced subgraph version of the conjecture isn't true for them, right? And if you look at bicliques, so the densest bipartite graphs, and there you can't get rid of all the 4 cycles. So I would think, what about the densest 4-cycle free bipartite graphs? Can you get rid of all the 6 cycles in the densest 4-cycle free bipartite graphs? And those graphs are regular. And so this proposition actually does apply to them. So this, I think, is the first piece of evidence. So the proposition is that if you give me d, k, and big D, which is sufficiently large as a function of d and k, then every d-regular bipartite graph satisfies the induced subgraph version of the conjecture. That is, either has KDD or a graph with average degree at least d, girth at least k, as an induced subgraph. So the proof of this is pretty easy, but also I think it's really pretty, and so I want to go through the proof. So the idea is that instead of including edges independently at random, we're going to include vertices independently at random. And the Kováry-Sauce-Turan theorem on the maximum number of edges in a KDD-free bipartite graph is exactly what's going to make this proof work. It's really quite exactly what you need. Okay. So I want to go through the proof just for the case where k equals 6, because it'll be a bit more illustrative, but really the same exact proof works for general k. And so that means we're trying to get rid of the 4 cycles of the graph. So here, d and k are fixed in the big O notation, and n is equal to half of the number of vertices in the graph, because since the graph is bipartite and regular, it has the same amount of vertices in each side. Okay, so we want to show that the graph has O of n to the d to the 3 minus 1 over d cycles of length 4. The idea is really just that we're going to save this extra minus 1 over d from what we'd usually get. So the number of edges of this graph is equal to n times d, because it's d regular and has n vertices on each side. And now we can just look at the number of 4 cycles containing a particular edge e. And so if we look at e, each 4 cycle comes exactly from an edge between a neighbor of v and a neighbor of u. So if you look at this graph here, which I'll call h, which is between the neighbors of u and the neighbors of v, then this number of 4 cycles containing e is actually equal to the number of edges in h. And then just right away by the Kováry-Sauce-Turan theorem, since there's about d vertices in each side of h, then that is O of d to the 2 minus 1 over d, assuming that you have no KDD. As in, either we win and we find our complete bipartite graph KDD, or we have this. So I should have said that this lemma is assuming that we have no KGD. Okay, good, but that proves it. And so then, just given this particular lemma, the same proof as before works. So you include each vertex independently at random with a particular probability, and it's pretty typical to do this sort of thing. So I'm fixing epsilon to be something sufficiently small and including each vertex independently at random with this probability. And then deleting one vertex from each cycle of length 4. So the number of vertices is, maybe I've deleted some, but certainly it's at most 2pn. And the number of edges, the expectation for the number of edges originally, right, is this p squared dn. And then canceling out one of the p's with the d, we get d to the epsilon pn. So far we're good, right? There's many more times edges than there are vertices in the graph, and so that's good. So far we expect it to be dense, as in to have large average degree. And so now we just need to bound the number of edges that we delete. And so we delete some edges which are incident to a 4 cycle, and some edges which are incident to a vertex in the 4 cycle but not actually contained in the 4 cycle. So this expectation of the number of deleted edges is upper bounded by the number of tuples like this, consisting of a cycle and an edge. And as is usual in this sort of thing, the configuration with more vertices wins. It's the bigger amount, so let's just look at that one. And it has 5 vertices, and so we get p to the 5th, the probability that all of those vertices are included. And now we just have to count the number of these. And so we're using the lemma from above, but then plus this vertex is incident to about d edges. So we gain a factor of d. That's n d to 4 minus 1 over d. And I'm again ignoring constant factors, and that's what I mean by the approximately equal. So we get this, and then again, taking a pn on the outside, we get this. And now just writing out what p is, this is pn times d, 4 to the epsilon minus 1 over d. The point here is that if we take epsilon to be really small, then the minus 1 over d wins. And in fact, this is little o of p to the n. So the point is that this is even less than the number of vertices. We really haven't deleted much of anything in terms of the edges whenever we get rid of this. So that works. Yeah, and I know that's a lot of calculations to go through, so it's sort of unfortunate, but I think that to make sure that the intuition really matches with what happens, I think that it's important. But the intuition is really just that counting this number of cycles and getting the minus 1 over d is exactly what makes this argument work. In fact, I've wondered if you can like relate, go in the other direction, and if you know that this is true, if you can then prove the Kovács-Ostrón theorem. They seem really like the same thing, but that's what I wanted to go through there. So that proof was pretty easy. We were able to sort of just do it, and in general, it's a lot easier to take care of regular graphs. So it's going to be important here to say something about the general theorem, about how we can get rid of 4 cycles and induce subgraphs unless we have a big biclique. So I've just stated the theorem again. There it is, and there are the pictures for the outcomes. So I want to go through the proof of this a little bit, just sketch it. Okay, so the new lemma is this, and that is for any fixed r and lambda, every bipartite graph of sufficiently large average degree is a function of r and lambda has an induced r lambda subgraph. And what I mean by that is that you can find a subgraph with bipartition AB, so that every vertex in A has degree exactly r. and so that A is at least lambda times B. The B is a lot smaller than A, as is drawn in the picture. And so the point here is that we're able to get one side to be regular. We can't get both sides to be regular. We know that that would be too much to ask for, but we can actually get one side to be entirely regular. This isn't really too surprising. There are well-known limits that say that you can get it close to being regular, but the point is we actually want it to be exact so that we can apply results on hypergraphs. And that's still not too hard. Sort of just a probabilistic argument works to get this. And the other thing to notice here is that our lambda subgraphs are dense already. So we know that every vertex in A has high degree, it has degree at least R, but also B is smaller than A. And so the average degree of B is at least R also. So now we're really just working with, and in general, we're always really just working with graphs where one side is regular. And so from there, the proof of Delmonica, Kubik, Martin, and Rodel actually works. It's included in the paper, and it's still quite short. It's only a couple of pages long. It's included in the paper because they write it for subgraphs, not induced subgraphs. So it's all self-contained there. I want to say a little bit about what this theorem of Fioretti is that they imply. And it's a theorem on hypergraphs, which is why we've reduced to the case where one side is regular. All right. So this is going to take me a couple slides to do, but I'm going to do it with all the pictures, so I hope that's all right. So, and I'm also going to state it informally, because I think getting the intuition is more important. So this theorem of Fioretti says that we can find a subset of A, which is still really large in comparison to A. Really large means it's at least like a constant fraction of the size of A, where that constant is going to depend on R, right, which is the side that A is R regular, and some other R prime, which is going to show up later. So without losing too much of A, we can partition B into R parts so that every vertex in A has exactly one neighbor in each part. And so that another Ramsey type condition holds. And that Ramsey type condition says that if you look at any BI and BJ, if you get a 4 cycle from BI and BJ, that is if you have this as a subgraph, that then in fact every vertex of BI and every vertex of BJ actually have a lot of common neighbors. They have at least R prime common neighbors. So if I look at another vertex in BI, it also has a lot of common neighbors, right? So they might not all be the same. Okay, so let me just say sort of again what we're trying to do. We're taking this larger side A, and then without getting rid of too much of A, we're partitioning B into parts so that every pair either contributes no 4 cycles or it contributes a lot, in the sense that every pair has at least R prime common neighbors. Okay, so then the idea of the proof from there is we have this A prime and we have the partition of B. The idea is to make a graph on R vertices from that, where BI and BJ are adjacent if they contribute a 4 cycle. And then there's 2 cases. Either we get a large stable set in this graph, and that way we can remove all 4 cycles. or we get a high degree vertex in this graph. And so I'm going to say something about the case where we get a high degree vertex. So let's just suppose that, say, BR shared a 4-cycle with every other BI, right? Something like this. Oops. Sorry, I didn't quite draw that correctly. Let's see if, sorry, let me say this. So BR shares a 4-cycle with every other BJ, so something like that. Okay. Then if we take any vertex in BR and look at its neighborhood, we know that every other vertex on the B side actually has at least R prime neighbors within there. And so every vertex on the B side has high degree, and still every vertex on the A side has high degree because each has exactly one neighbor in BI. And so the point is that now we can sort of repeat the arguments again and again, and if this possibility happens too many times, we get a big biclique. So without saying anything more technical about that, let me just say something more general, which is that triangles and 4-cycles are special. And let me say why that is. So, and like why you shouldn't get any other special cases for induced subgraphs. And the idea is that either you find a helpful vertex or you win immediately. And by win, I mean you find an induced subgraph of high girth and high average degree. And so we saw that by using Ferretti's theorem, we saw that maybe we can find a vertex that has a neighborhood so that there's a dense graph between its neighbors and some things on the other side. And then if you repeat this too often, you get a big biclique. And likewise, in the Kwan, Lester, Sudakov, and Tran proof, they have a special case where maybe you find a vertex which has a dense neighborhood. And then by repeating this too many times, you get a big clique. And so the point is that the proofs, every proof I know of even the subgraph results, really work especially in the case where there's a big clique or a big biclique. Right, you can really kind of see this showing up in the proofs. So as in, even though in proofs of the non-induced version, you don't find an induced subgraph, you still do either find a clique or a biclique. That really does still show up in the proofs. And so what I've said so far in the talk is all that's known in general about Thomassen's conjecture. And I think that this is the reason why. As in, I think that if you could get rid of the 6 cycles, you could prove Thomassen's conjecture in general, right? Because these cases that are known so far on Thomassen's conjecture are really different. And this induced subgraph version tells you why and what's different about them. And so I still think that Thomassen's conjecture would be really quite hard, but I'm tempted to work on it more seriously because of this, right? I think that the natural thing to do whenever you try and work on Thomassen's conjecture is to mimic the proofs of the previous cases, and that would let you like find a helpful vertex as one case where you win. And I think that this like what we've seen so far in the talk shows that that's not going to happen later on. There's no find a special vertex case. You should really just look to win immediately by finding an induced subgraph. Okay, I want to say a little bit more about what makes Thomassen's conjecture difficult. So far, the first part of the talk is about what's known and what are the results. But now I want to talk a little bit more generally about what makes Thomassen's conjecture difficult. And again, it comes down to regular graphs. So I mentioned before that you can't reduce the problem to regular graphs. And now I want to say that it's worse than that. It's actually much worse than that. you can't reduce the problem to graphs with maximum degree bounded as any function of their average degree. So the formal statement of that is this, and it's that for any d in delta, there's a graph of average degree at least d with no subgraph of average degree even at least 8 and maximum degree at most delta. It's just awful. You can't even get close. And this is due to, again, Delmonica, Kubik, Martin, and Roble, but they're adjusting a well-known construction of Piper, Rodel, and Semiretti. And so the one thing that's known about Thomassen's conjecture, which isn't known about the induced subgraphs version, is if the maximum degree is bounded by, say, a singly exponential function in the average degree, or even a little better than that, you can almost get up to doubly exponential, then Thomassen's conjecture is known. But this theorem says that that kind of result has no chance of proving the general conjecture. And the theorem I just mentioned is by Delmonica and Rodel. So I want to talk about how you might try and get around this problem. So it's a concrete problem that seems really, really difficult, but at least it's more concrete than Thomassen's conjecture. Okay, so we know that we can reduce to graphs which are regular on one side. And the construction of Delmonica, really of Peibel, Rodel, and Semiretti, has another property. Approximately another property, and I'm going to make that property exact. And that is that you can partition, again, this side B into R parts, so that each vertex in A has a neighbor in exactly, has one neighbor in each of the parts, and also so that every vertex in B1 has degree D1, and every vertex in B2 has degree D2, and so on, and every vertex in BR has degree DR. So what I'm saying is not only does every vertex in A have the same degree R, but also all of its neighbors have the same degrees, and it sees one neighbor of degree D1 and one of degree D2 up to DR. And this is hardest when R is a lot smaller than D1, so on, right? Whenever these degrees are really, really, really different. And I'm interested in if these graphs satisfy Thomassen's conjecture. And I'm even going to let you say that D1 is as much larger than R as you'd like, and D2 is as much larger than D1 as you'd like, and so on. And this is really tricky because the random constructions tend to have a few short cycles already, as in like smaller than n. But it seems like you can't get a counterexample by using random graphs, to me at least. But yet I have no idea how to actually prove this, even though it's quite concrete. So I think this is maybe the most interesting case remaining for Thomassen's conjecture. And then there's one other thing I want to talk about, which is that all of these problems work well for the chromatic number as well. So the chromatic number being the minimum number of colors it takes so that no two edges are joined versus the same color. So for case 6, chromatic number 6, and for complete bipartite graphs, they have chromatic number 2. So what I'm pointing out here is that while we said that we won if we found big bicliques before because they have high average degree, for the chromatic number problems, we don't actually win if we find big bicliques because the chromatic number is still small. But we can't even do the first case for induced subgraphs. That is, so Rodel proved that for any D, every graph with chromatic number sufficiently large as a function of D has a triangle-free subgraph of chromatic number at least D. And then there's a question, I think it's due to Esperet, but if anyone knows, because I haven't actually seen this in a paper, so if anyone has a better reference for where this actually comes from, I'd like to hear it. But it's a question that Does this hold for induced subgraphs in the absence of a big complete graph? And this seems incredibly hard. I don't know of a way of approaching this, but I do wonder if some of the recent techniques for finding induced bipartite graphs could be at all helpful for this. And finally, you can't push this further because of Berlin graphs, as in you can't try and find, if you replace triangle free with large girth, that isn't going to work. And so I don't know if there's a good conjecture for where to go after this. All right, thank you.
Thank you very much, Rose. I guess we can unmute ourselves and clap. Are there any questions or comments? I have a quick. Actually, I have two questions. One is in the last slide when you said that this cannot be extended to graphs of large girths. Do you mean the induced version or even the non-induced?
Yes, I mean the induced version. Yeah, the induced version. I haven't thought about the non-induced version.
Is it a conjecture?
I mean, I would check Berlin graphs.
Mm-hmm.
Yeah, so this I didn't even want to write it as a conjecture because I couldn't remember an actual like written source for it. But maybe someone in chat might know. If this goes up to the level of conjecture.
Yeah, I also had another question about this theorem of fluidity you mentioned. The statement seems weirdly regularity-like. Is it in any way related? I mean, like, dense enough for actual regularity limit to be relevant, but it really seems kind of like
I don't think so, because they're just constantly dense. And that's sort of the problem with this area. I mean, there's been recent work by Kudakrov and Pokrovsky and some other people on trying to really improve this function. Let me see if I can go back to the page where it would have the function. So this 4-cycle function from the Kuhn and Ossis results, what this is. Like if you want to say anything about the dense setting, whenever it's actually really dense, isn't like quadratically dense, then you really need to improve this to be a polynomial or something like that. And so they've worked on that, but so far the bounds are still exponential. And so yeah, it seems to me that there's really a difference between this sort of sparsely dense setting where your average degree is at least a given constant versus actually being dense in terms of having a quadratic number of edges.
Right. Are there any more questions?
Rose, what's known on Thomassen's original conjecture? Like, is it true for any special class of graphs?
I think there's one paper working on expanders that finds spanning subgraphs without 4 cycles, but I don't know of any other results for classes of graphs. As in, I'm sure that there are some classes of graphs where it's easy, but I don't know of any actual paper that has that as the focus.
Right, thanks.
Yeah, I guess what about random graphs? Presumably for them this should be not hard.
That's true, yeah. Yeah. Yeah, somehow as long as you don't have this type of, oops, it's all the way at the end, of obstruction, then you should probably be able to do it by just finding regular subgraphs.
Did you go to the last question on the last slide again?
And I mean, another thing I guess I tend to think about these is like line graphs. So in the sense of Like in some complexity theoretic cases, line graphs are as hard to deal with as all graphs, and sometimes it might be interesting to think about whether or not this is true for line graphs, but maybe it's easy, right? Because you'd just be bounding the degree.
Any more questions? If there aren't any more questions, then let's thank Rose again. We're gonna meet again next week, and our next week's speaker is Zixia Song from University of Central Florida.